Here is your paragraph punctuated properly for clarity and readability. It's the question that always comes up when thinking about the origin of the universe. What came before the Big Bang? If there was no air before, or what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including the young Albert Einstein, assumed the universe itself to be eternal and everlasting. Of course, stars could be born and die, planets could collide, and civilizations could arise and fall. But on large spatial scales and over long periods of time, it always looked roughly the same as it does now. Only in the 1930s did convincing evidence of the expansion of the universe appear, and in the 1960s, its origin in the Big Bang was confirmed. Such a radical revolution in the scientific worldview had not occurred since the recognition of the heliocentric system. But then two equally difficult questions arose. First, what actually was before the Big Bang? What was space like before it began to expand? And how long did it stay in this primordial state? Secondly, everything that has a beginning has an end. So what will it be like at the end of our universe? The English physicist Brian Cox set out to find an answer to these questions. Now, in a world-shattering revelation, Cox has declared that he strongly suspects that the universe existed before the Big Bang, throwing the theory of our origins on its head. We used to think that the universe emerged in that state, very hot and very dense, at the beginning of time, and we used to call it the Big Bang. But now we strongly suspect that the universe existed before that. In that sense, it's possible to speak of a time before the Big Bang. Join us as we dig deep into how Brian Cox just debunked the Big Bang. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to everyone, regularly contributing to public debate and discussion. Never one to shy away from the big questions, Cox previously took on the story of the Big Bang. The idea of the Big Bang first came about back in the 1920s and 1930s, when we looked out at distant galaxies and discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing toward one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding. Today, if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart. It also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, that means the universe cools as we age. Hence, things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backward in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart, a time where matter and antimatter pairs could spontaneously form, as the universe was so energetic that pairs of particles and antiparticles could spontaneously be created, a time where individual protons and neutrons break down into a quark gluon plasma, as the temperatures and densities were so high that the universe becomes denser than the inside of an atomic nucleus, and finally, a time where the density and temperature rise to infinite values, as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, the singularity that represents where the laws of physics break down, is also understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark gluon plasmas in the lab. We've created matter-antimatter pairs. We've done the calculations for which light elements should form and what abundance during the early stages of the universe, made the measurements, and found that they matched with the Big Bang's predictions. Coming forward even farther, measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures, like stars and galaxies, form and grow. Everywhere we look, we find tremendous agreement between theory and observation. The Big Bang looks like a winner, except in a few regards. 3 specific things you would expect from the Big Bang didn't happen. First off, the horizon problem. If we look in different directions, we see the universe as having the same temperature and density everywhere. But even since the start of the hot Big Bang, these regions never had time to communicate, exchange information, or reach thermal equilibrium with one another. So, how did they evolve to reach the same temperature and conditions everywhere? Next, the flatness problem. In an expanding universe, in general, there's a fight between the initial expansion rate that drives things apart and the gravitational effects that work to bring everything back together. In our universe, we observe that these 2 opposing forces are pretty much perfectly balanced, leading to an exactly spatially flat universe. So, why was our universe born with those properties? And last, the monopole problem. If the universe reached these arbitrarily high temperature and energy conditions, then why are there no exotic leftover heavy relics, right-handed neutrinos, magnetic monopoles, and other particles that should be observable and left over today? We can always shrug our shoulders and mutter something like, those must have just been the initial conditions, or that's just the way the universe was born. But that runs counter to the enterprise of science. Instead, we look for a mechanism that would mandate and set up these conditions. That mechanism sprung forth in 1980 in a remarkable paper by Alan Guth, who noted explicitly that an early, rapid, and relentless phase of exponential expansion, where the universe's energy was not distributed among matter and radiation quanta, but rather was inherent to the fabric of space itself, would solve all 3 of these problems. But because inflation represents an exponential expansion of space, rather than one that terminates in singularity like the original model for Big Bang, it sets up a very different picture at the beginning, a whoosh that led to a Big Bang, rather than the emergence of time and space from a singular state. Now we get to address the really big questions. What does all of this mean for the true beginning of the universe? If such a thing even existed,